You are able to operate those things, right? Yeah. But maybe go there, you may have to switch on the light. Just might want to figure out
the bottom right. Want to switch off or
Switch on, all are switch off at least.
I think okay, actually let us start. Happy to have Tulsiram Reddy from New Delhi, India. And so he'll be speaking about zeros of sums of random polynomials, continuing further on random polynomials. Thanks, Tulsi.
Thank you, Yogesh and organizer. This is joint work with Sean Roth. So several discussions with Kaushik and Manjunath there much before the
Can you speak a bit louder? I
okay.
can't hear.
Is it better?
Yeah.
Yeah, so this is joint work with Sean Roth, and also there were several discussions and several discussions on this problem. Manjunath and Kaushik, before we did this on the same problem. So let me start with the problem.
No, once you just.
Let me start the problem. Suppose you have two polynomials, P and Z and Q and Z, where the roots or zeros of the polynomial are specified. They are IID coming from measures mu uniform measures mu and mu. Okay. So we know the zeros of these two polynomials, Pn and Qn. Sequence of polynomials with zeros we know sort of their ID and then. So I put a uniform measure on the zero set of this polynomial. See where does this come in? So this will be two set of the. So if I put a uniform measure on the zeros of these polynomials, this converges to the measure from which these random variables are drawn. Same with y. And throughout the talk we use this notation because if you look at it, log mod 3n z is equal to summation log mod z minus, right? And if you take an approach here, this is, I think there is a factor of 1/2, right? That must at xi over n, so that it is a probability measure. So throughout this, this identity is useful throughout the talk, and we use this extensively.
Xi is yi is a complex value.
Yeah, complex. Yeah,
So
HHY
everything is
is a complex value. In general, you can also restrict it to real as well, but we take measures on the complex value. So, natural question to ask: what happens to the zeros of the product of these polynomials? Let me say something. Of course, the answer is trivial. The zeros are just enumeration of x1 to xn and y1 to yn. Now, if you put a uniform measure on that, a similar result will hold by giving the mixture of these two measures. Uniform mixture of these two measures. Now, can we answer the same thing for when we take the sum of the two polynomials, Pn plus Qn? First of all, is it determined by just mu and mu alone? If so, what is the relation between mu and mu that would give the limiting measure of this new polynomial Pn plus Qn? So that is the question. So one other motivation for this problem is, in random matrix theory, we have this notion called free convolution. So what does this mean? So for simple random variables, we all know what a convolution is. We can compute the convolution of two random variables or two measures. But in random matrix theory, something happens. So if you take an, Bn, two matrices whose limiting EST this converges to mu. So this is eigenvalues. And this converges to mu. If you know this, then n plus empirical spectral distribution of this. This converges to a measure which is determined by mu and mu, denoted by what is called reconvolution. So this is just the uniform measure on the eigenvalues of the sum of A plus B. And UN is so in random matrix theory, we know this result, it's well studied and well understood. So what is free convolution? It is just um, so there is a thing called R transform. For any measure, you can define what is called as an R transform. Free convolution of U and mu is determined by the sum of the R transforms. So you can pull back the measure from the sum of the R transforms. From there, you can get the free convolution. In other words, think it's just if you take the cumulants and add and read the measure, look back to the measure, you will get that what is free convolution, the free convolution resultant measure. So in some sense, we want to find if there is some such operation for random particles. So it turns out the answer is green. But unlike convolutions, it is similar in many senses, but it also doesn't have certain properties. You'll see the answer and then see what. There are analog. Before that, at least for next 10-15 minutes, I'll do some class 4 complex analysis. Let's try to work out some examples. This is completely deterministic case. So we can always study this problem in the deterministic sense. You don't need to put random variables. You can still ask sequence of polynomials where the uniform measure on the zero set converges to mu and vice versa converges to mu and ask the same question. So that you can start with when mu equal to uniform on S1 and mu is uniform on twice, that is circle of radius 2, then what will happen? Of course, this is the random analog, but let's work out what happens to the deterministic. So the polynomials are then power n minus 1 minus 2. This equal to 0 and roots of it. So if you let n go to infinity, so this becomes so you will get a uniform measure on the largest. You take polynomials whose roots are distributed on the two concentric circles, the resultant measure would be a uniform measure on the largest circle. So for another example, somewhat interesting, you take two discs, disjoint discs, put a uniform measure on two disjoint discs, then you ask the same question, what will happen? Disjoint disc. It turns out the answer is the measure will support on the y-axis. Basically, it's the perpendicular bisector of the line joining the centers of the disk. And the measure can be calculated explicitly. It turns out to be it's Cauchy on y-axis, Cauchy distribution. I don't remember. It depends on the length of the distance between the two centers, but I don't remember the exact factor. But it's some scaled Cauchy on the y-axis. So as a warm-up, I mean, handling the uniform or deterministic analog, handling the uniform on the disk is a bit hard. We'll just do for so the answer is same for disk or circles, disjoint circles. We just do computation for the circles. Just to convince you. Take PLZ. Circles, or even you can put a dot. So I think I'll just do the dot. I think that's easy to compute. So you just put so mu1 is Dirac mass at 1 and mu is Dirac mass at -1. The answer is same for disk circles or even point masses. So it only depends on the center, so long as they are disjoint. Take the sum. Okay. Is correct.
Minus of WK plus 1 by WK minus 1.
Now, what is this? You can compute this. This turns out to be cotangent theta by 2 where theta k by 2 where theta k is equal. So when you have unit roots of unity as n tends to infinity, the argument of this roots is uniform on for theta between 0 and 2 pi. So this theta k as n tends to infinity. This converges to uniform measure of 0 to pi, and cotangent of uniform is Cauchy. I think there is an I or minus I. Can check that. That's why you get Cauchy on.
In these cases, is it clear that it is well defined? That is, I have some other sequence Pn which converges to mu and has some other sequence Qn whose zero sets converges.
So
to
okay, so the claim is that for random polynomials, this is true. So this is more like a demonstration of it. I'm not claiming that this is true for every deterministic. Maybe it is true.
But there are examples where it fails, or
Yeah. So otherwise, the result is it doesn't make sense to state a random. So you can also do this experiment further. You can do more convolutions. You take point masses on this, or what happens is you will get this on these diagonal bisectors. I don't know what these can be called, sort of, but you understand these are bisectors of these sides of this polygon that is formed by these points. And so when there are two, we have Cauchy on this line. It is natural to expect sort of this will be supported on these bisectors. But what are these? So this is sort of some sense square root of Cauchy. This is in some sense the square root of Cauchy, because you get that proportion of zeros going here, and similarly that proportion of zeros going here.
In the previous example, you had taken two discs, size were the same. If one of the disc is bigger,
Doesn't matter. So long as they are disjoint, it doesn't.
still be the Cauchy on the
Yeah.
bisector.
So long as they are disjoint, it all that matters is where the centers are.
Would they have to be discs?
We'll see. I mean, I'll formulate a general result. The answer is encoded in that, like, encoded in the result, in the sense like why it works for, why the answer is same for disks or points or circles. Or, I mean, it needs to be somewhat rotationally invariant, otherwise the measure has to be rotationally invariant. And if it is not uniform or something, then I think instead of Cauchy, you'll get something. So yeah, you can play with it and get all sorts of interesting pictures and all. But let's so this is the warm up. So let's go to the actual result. So okay, Yogesh asked, is there an example where it fails, right? So I mean, I'm stating a result in probabilistic result. I have to give an example where it fails for the deterministic case. That means gave you examples, several examples where this sort of where we can compute it for the deterministic case. So I'll give an example. I think it's better after I state the theorem, because let me state the theorem. What the answer is? The answer is actually encoded in the logarithmic potentials. So assume mu is not supported on a circle. So this is sort of an assumption. I think one can drop the assumption, prove the full thing. So that sort of reverse engineer put that assumption. For our theorem, this assumption is required, but there are several students who can tighten the slack here. There exists, yeah. You are in the same setup. Then look at the zeros of Pn and Qn. Then there exists a row which is determined by the Laplacian of maximum of u mu and v. I think I did not define u mu and mu. It's not. Let me define what u mu and mu and z is integral of f minus w. So this is log. It is a well-studied object in complex analysis in potential theory. This is called log potential. If you look at this u mu, if you look at u mu, if you carefully stare at it, it is like this object here. If you take n tends to infinity by law of large numbers, this should go to this. This is the sort of continuum analog of this. It's natural to expect that if you take Laplacian of this, you'll recover the corresponding measure, the limiting measure of this. Of course, this is not formal. One can formalize this, but I will not go into those details. Just want to give the intuition. So the resultant measure, that is the resultant measure for the sum of polynomials is given by this maximum of u mu and u mu. That's the answer for that.
There's no condition on new.
No conditional. If one is not on circle, that's it.
One of the two should not be.
Yeah. The statement is clear.
Sorry, I missed lambda. Lambda is last d lambda.
D lambda is, oh sorry, lambda is Lebesgue. Few notations.
Yeah. And in the deterministic, you always wrote it as mu circle mu, like a.
Yeah, that. Okay.
So that is not. This is.
Yeah, this is what it is.
For the definition of that mu circle.
Mu is maximum of
Rho.
this. Yeah, Laplacian of maximum of this. Of course, what does it mean to be Laplacian? Laplacian means is defined via this. Like for any test function, you can exchange the Laplacian and you can exchange the Laplacian and this identity codes. Sort of identity codes for any test function. Like you exchange the Laplacian from the two. Yeah, and this result again, there is one more place where there is some slack. We can only show this in probability. I mean, most of the results in random polynomials these days prove almost sure. Again, there is some slack there. That's the main result. I'll give a very broad idea and sketch of the proof for the rest of it. Yeah, I mean, okay, now that I gave the result, maybe I should give the example where it doesn't, where this doesn't hold. This is what we expect for random polynomials. Give an example where this fails, the deterministic case.
So the cases you showed are cases where it is working, right?
Yeah, where it is working. So I will give an example where the resultant measure will not be this.
It may not be entirely clear what that in those cases this is describing what you showed. Are you able to explain?
Yeah.
Okay, continue.
Yeah, maybe I will compute. I'll try to compute at least for for this one. Equal to uniform. Equal to this one. That is and there is a minus somewhere. Generally, we put a minus here.
This is a matter of convention if you want it.
Yeah, I think
You want it to be subharmonic, I mean,
yeah, I think we need a minus. The minus is required. Then in this case, the maximum.
No, maybe you see you need without the minus sign because you want the two things to be subharmonic and then the distributional Laplacian of that. This is superharmonic. So you want then you can't take the maximum. So conjugate just
Subharmonics is subharmonic. You want to choose the.
Yeah.
I mean, anyway, those are log mod Z is anyway, there it's anyway harmonic, but okay, fine.
it's okay, right?
And mod
It's not okay.
No, between it would be mu, right? It would be mu would be the max.
Max has to in the annular region.
Yeah.
Z is positive. In the annular region. And he doesn't want that. At least by the claim.
Let me get back to that later, but modulo minus sign.
Actually, it's fine. Minus is also fine. No, it's a continuous function. The first one is a continuous function. It's log mod Z is harmonic outside the.
No,
So-
but then you wanted the measure is for the maximum of that.
That's fine. I'm saying it will still be subharmonic. It's continuous. At least the first function, it's continuous, right?
Yeah, it won't be, it's continuous, yes.
Correct. And outside of the origin, anyway, it's harmonic.
Yes.
So plus or minus doesn't matter in terms of subharmonicity.
Not on origin, on the boundary is the problem.
Right.
Inside it is harmonic, outside it is harmonic.
On,
It's continuous, right?
on z equal to 1. It's not.
There is a problem. But then the max is not working out.
I think. Okay, I'll should get back.
Maximum is for the, so your theorem was that the potential is that of the larger, which is,
No. Inside it won't be zero here. Log was another one, right? And this second one.
yeah.
No, one way.
No, log 2 there.
Log to there. Okay, second one.
Second
Second one. No. In the
Yeah,
disk.
disk of radius 2 and this log 2. Inside the disk, log are inside and
Log 2. So
yeah.
max will be that.
it's, yeah, log 2 for inside the disk and
To verify this.
No, that's fine. Yeah, this looks. I guess the second one is also continuous. Has to be continuous, right? Which it wasn't earlier. Yeah.
Now. Is n plus z is just z power n minus. Doesn't matter. So the corresponding measure here. So star is so if we use the maximum mu, given that mu and mu are same, the resultant should be the same. Whereas when you add, you are getting just z power n, the resultant is just example. Quickly show the sketch of the proof. Majorly so the key idea is to estimate this log mod Pn plus Qn with 1 by n log mod Pn max with Qn. This is the estimate we need to get. Once we have this, we push through the limits and various other conditions. But for fixed Z, for almost every Z, we show this in probability. With probability going to 1, we show this. If you have this, we have the result. So you push the limit, you get log maximum of u mu. So you go into two mediums. In general, this is not true. There will be places where these two are sort of and so
Your parenthesis is like your parenthesis should be after comparable, right? Bracket should be after comparable, where you end the bracket.
yeah. Several mistakes. Like, I'm very rusty going on. So yeah, so the quantitative version of this statement is probability that the ratio is between 2 and 1 by 2 is quite small. This goes to 0 as intent statement. Now, once we know this, fixed set almost. And for fixed set, we show it for almost every set, that is in the Lebesgue cells.
Yeah, you move us.
Then you have some tightness criteria. I'm not going to tell that. It's some estimates. It's not hard. One has to. It's also some boring estimates. Not boring. Once you have this fixed set and along with tightness criteria, we have. So
Where in this condition did you use mu is not supported on sub?
yeah, I think I'll explain the proof there. Fix a Z that is not an atom of mu or mu, and a sample point not in this set, that is when Pn and Qn are comparable. In that set, when Pn and Qn are not comparable and Z is not an atom of mu or mu, then assume Pn is the maximizer for that particular set. Then log mod Pn plus Qn is log mod Pn plus log mod Qn by Pn. And we are outside this region. In that, for that sample point, this is log mod. So Pn is just Pn max Qn. And this is all that we need to show now is this probability is found. The probability of this set is found. To show that, we use a very well-known inequality or Kolmogorov-Rogers inequality. So for that, we need to define what is called as a concentration function. This was already discussed in the course of these lectures by Mokshay. So this is nothing but the concentration function of x in a ball of delta is nothing but the maximum mass it can accommodate in a ball of radius delta. So once we know, so we want to bound the concentration function for the sum of IID. Here it's not a IID, but in our case we have IID, sum of IID random variables with individual concentration. So what we will show is here, 1 minus the concentration function of xi delta I is non-zero. Shows this is bounded away from 0. And this again delta is bounded away, delta i's are bounded away. In fact, we take all delta i's to be one, same. Then we have C over root n bound. So we use this result, we apply that, and all we need to show now is to show that there exists a delta and all, that this is we can write this expression in terms by applying logarithms, log mod pn minus log mod qn, and this is bounded by concentration function of log mod pn z with a radius of 2. I'm just conditioning on qn. Pn and qn are perfect. And log mod pn is sum of ideal elements. Log mod pn is sum of log mod z minus xi. This is sum of ideal elements. So we are in the setting of, we need to bound this. We are in the setting of Kolmogorov 0 statement. Kolmogorov 0, we bound this by, if you use 2, we will not achieve anything. We need to use something much less than 100. So this in the statement, often many times it works for this delta itself. You don't need delta, but you need to use something much smaller than delta. Yeah, so all we need to show is that this is non-zero. There is an epsilon for which, epsilon positive for which this is non-zero. This is true because we are, if you think about this, if you go outside the atoms, it's a non-atomic thing, and once you go for almost everything, you can keep shrinking, and you can always find an epsilon value. Since in these places the not supported on circle is required. Otherwise, you can have a measure on circle and still have this too.
Not z minus x1 can be written there. That's what you are saying. If it's supported on the circle.
Yeah. That's the argument. And there are extensions of this. This was done by Bangalore, then Cross. Recent work. So what they do look at is so removing that assumption, but they add another assumption in the sense on the moments of movement. Yes. So this result one can show for, assume log plus movement, finite log plus movement. For that one can show this result, but it's a bit more general in the sense you don't need the full degree of Pn and Qn. Qn can be, for example, a polynomial of degree 1. Then also you can. So the degree of Qn can be C times n. You can use that, and what happens is here that C appears here. That C can be between 0 and 1. It can be 0, it can be 1. can also be 0. So essentially, thematically it's the same. Only difference is it's not, instead of, so what we do is we are taking maximum of mod Pn and mod Qn. Rather, we should take maximum of 1 by n mod Pn and 1 by m mod Qn. That's all we need. That's all we need to change and work on it. So previously we are just give the intuition why this is true. So we are writing 1 by n log mod nz plus right, 1 by that is what we were using, but instead of this, we need to use maximum of 1 by m. Here in this case, 1 by c times m log mod. This is the right approximation, and this approximation works even for c equal to c. So, I mean, in a way, it's surprising because you can take Pn to be, at least the example they give in the paper is, you can take mu to be uniform on unit disk. And Qz is just z minus some 10 or something, just take some finite polynomial. And if you perturb this polynomial with this factor, with this additive factor, you will no longer be getting, I mean, although it's appears very small, you will no longer be with this mu. What you will have is, so this will, the resultant would be uniform on
It is 1 over n there, right? And what is C? C is, we are taking the degree to be Cn.
Yeah.
Yeah, Cn is, isn't degree Cn? Degree
Yeah,
of
degree is
Cn.
here.
Here it is 1.
Where is it from?
Okay, C, you're taking C to be 1 by n.
In this case, here I think C is 0 actually. Anyway.
Yeah.
So maybe, yeah.
Yeah, but when C is 0, it is u mu, right? Max of u mu and C u mu is u mu. When C is 0,
Max of, it's just the max of u mu and 0.
okay, max of that means 0.
Yeah. C times u.
Negative part goes away.
Yeah. What will happen is the entire mask, you perturb this large polynomial with this small additive perturbation, with this small polynomial. The entire measure goes and sits on the unit circle.
And there you meant C over n or 1 over C?
1 over C times n.
Taking the degree.
So if you just, so previously we were not carrying this 1 by n. You need to look at the normalized log.
It must be 1 over n itself, right? Your logic is one of the two will be large, right? Not both. Pn plus Qn is like mod Pn max mod Qn.
No, here it's 1 by n log mod Pn max 1 by Cn log mod QC.
Must be 1 by n. Right? Then you write it as C by Cn. Times C times C. No, no, man.
Okay. That's the only extension on this direction. That's the working out of this example.
Any questions? Yes.
We just go the condition. So that is the previous. So that condition is okay for any compactly supported compressors, right?
Which condition? Yeah. For heavy tail and all these caution.
No, get all that. Compactly, so there is no conditions at all here.
Yeah, actually, yes, that's right.
So the circle is not, so that is,
Compactly supported circle.
that is
Yeah,
removed.
so
Supported is fine.
So as I said, the statements are not perfect. There can be improvisation. The statements are tuned based on what we can prove.
So, sorry, is there anything known if you take finite k-many sums instead of two?
Instead
You
of
are taking the sum of two polynomials.
yeah, all these results you can do P1, P2, Pn, Pk. Yeah, I mean it's associative. And
The resulting measure will be measures of
it's just maximum of all these potentials. You can take from 10 measure.
Question related to some of your example and also the proof sketch you gave, you used only the randomness of one of them, at least in the
Yeah.
proof sketch.
In a way, yeah.
Is that correct of the whole proof?
I
You use Kolmogorov was in
yeah
these
for
things
only
you
one.
use
Yes,
it
that's
as
right.
the-
Yeah, sort of yes. Yes.
Maybe it's
Yeah. No.
No, I
No,
think
I'm
he's
not
doing
sure, I'm not sure.
symmetric Probably both ways.
No, because there are several parts I skipped actually.
yeah.
So there are several estimates one need to go the
So
other.
they also assume the same IID randomness for
Yeah, here also
Yeah.
IID and
IID
Yeah, in the same setup.
for both P and Q.
in the same setup.
Okay, so if there are no more questions,